Hello everybody and welcome to The Professional Noob. Like the channel name says, I'm a noob when it comes to 3D printing. I never owned one, I never printed with one, but I do have a background in engineering, mechanics, electronics, and automation control. My aim here is to help other noobs like me set up their own projects, be it 3D printers or other DIY stuff that they need around the house. So let's start off with this. Why would somebody need a 3D printer? And I'm gonna actually go and talk about my case because that's the one I know best, of course. Last year, I went ahead and built an automation project that would control my AC unit given a temperature sensor in the room, and they both ended up on breadboards with wires hanging out. They worked great, but they looked like crap. So I really wanted to give them some nice 3D printed cases. Of course, I could have gone out to a local 3D printing shop and built cases for them, but then I would run into the same problem whenever I would have another project that I needed a case for. Besides, I really wanted to experiment with different shapes and sizes for those cases. So for a while, I just let the project aside because either way winter came and both of these electronics ended up in a drawer somewhere because I really didn't need my AC during the winter. But then, ever since I was stuck at home at the beginning of 2020, I needed some tinkering projects to work on, and the case problem reappeared basically. That's when I decided to buy a 3D printer. Not only did I sort of need it, but I thought I could provide that kind of service to people in my local area as well, because there are lots of people who need 3D printed parts. In the longer run, I wanted to provide an online automated 3D printing service as well, where you would upload your models and get the 3D printed parts directly delivered to your door. But we'll talk about that later, probably in another video. That leads us to the problem, how exactly do you choose a 3D printer? And I think that choice is a very personal one, and it depends a lot on what you want to do with it, on your budget, on a lot of different personal factors. So I wanted a 3D printer, but I had no idea where to start. I looked at off-the-shelf options, reading reviews about them and watching a lot of online videos and other resources just to learn as much as I could. I would have surely bought a Prusa Mini, but the lead time on that was measured in months at the time. So I thought to myself, why not just gather the parts and assemble it yourself? That's where a very time-consuming journey began. At each step of the way, I would learn about a new term or new technology, and I would have to dig into that and learn more about it. My engineering background helped, but it's not crucial as you can learn about mostly anything online these days. The point is, I'm trying to help people understand the things that I've learned about in the past couple of months so that if you want to 3D print it yourself, you can just have a quick summary of what's what. So, as far as I've learned, there are three major types of 3D printers out there: SLS, SLA, and FDM or FFF. SLS, which stands for Selective Laser Sintering, are printers that are usually industrial grade and not meant for hobbyists. They cost a hell of a lot, and the material that they print also costs a lot. They use a high-power laser to sinter or fuse together a sort of powder, layer by layer, until a certain piece gets constructed. This process makes it possible to build any shape, as any layer that is cured sits on top of the rest of the powder-like material, so you don't have to worry about gravity making it all fall to pieces. The printed results are extremely detailed, but both the printers and the printing material are extremely expensive, which is usually something that hobbyists cannot afford. Okay, what about SLA printers? SLA stands for Stereolithography, and they work by hitting a UV-sensitive resin with a UV beam of light until that resin cures to a solid. These printers work by sinking a horizontal build surface in a vat or a reservoir full of liquid, but the bottom of that vat is transparent so that the UV light can shine through and cure each layer of the build, solidifying it and sticking it to the layer above or to the build plate for the first layer itself. And then that build plate goes up layer by layer and draws out of the vat a 3D printed part. As opposed to SLS printers, you need to have some means of supporting whatever overhang there is from the build plate, because otherwise they would just have to sit in midair, and that's impossible. It's fascinating to see one of these printers at work, as they seem to draw that printed piece out of a bottomless vat of liquid. The resins used are toxic, and they do require some care when handling them. Both the SLA printers and the resins used are a lot less expensive than their SLS counterparts. The problem is that the more accessible resins are not very tough, so you need to make a compromise between cost and functionality. The detail level of the printed parts, though, is usually very, very good. The last type of printers that I wanted to talk about are by far the most common among hobbyists. They're called fused deposition modeling or fused filament fabrication, FDM or FFF. That's a mouthful. The difference between those terms is merely a copyright issue. They're basically very precise and automatic hot glue guns. They work by melting filament and squeezing it through a hot extruder, as it's called, depositing layers upon layers wherever the extruder moves. Due to their relative simplicity, to the availability of the components, and to the pretty low price of the filaments, they are excellent for affordable DIY projects, even more so since there is a very large community that has used them and that can help out with any problems that you may encounter along the way. A notable mention here is that this type of printers has the lowest print resolution, which translates to the lowest quality printed parts, but you still get excellent quality for a decent price compared to the SLS printers, and you get pretty functional prints for the money you're paying compared to the SLA ones. You can get off-the-shelf FDM printers, but they usually tend to be a bit more expensive, and sometimes you get locked into whatever that vendor offers as replacement components, so I decided to build one myself. Now, in order to get the best quality that I could afford, I needed to dig into each of the components and see which of them makes the most difference to the final end result, the print. Okay, so first up, the extruder. That's the part that takes in the filament, melts it, squeezes it through a tight nozzle here, and then moves that nozzle around to deposit melted filament in layers to create the actual print. There are 2 or 3 types of extruders available. One of them is direct drive, and then there's Bowden, and then there's remote drive, which is sort of like a hybrid of the first 2. I haven't got the experience to choose one yet, so my idea when designing and choosing the printer that I want is to be able to swap these later on to experiment with all of them and see which one works best for me. Regardless of the type though, the bottom line is that the lighter the extruder, the faster it can travel without wobbling when it stops, which creates better quality prints. You need to be able to precisely move the printing head on all 3 axes or in 3 directions, hence the 3D term, to be able to deposit filament exactly where it's needed. And in order to do that, you have to have a very precise way of moving the printing head. And you can do that using a precise type of electric motor called a stepper motor. What these guys do is that they have a very precise angle set that they rotate with at each turn or at each step, turning that rotational movement into linear movement by using either threaded rods or a system of belts and pulleys. Traditionally, you have one of these guys taking care of the motion for each individual axis. So you have one stepper for the x-axis, one stepper for the y-axis, and one stepper for the z-axis. And this is called a Cartesian or orthogonal system. Also, traditionally, you don't usually have the printing head move on the y-axis. It's usually the printing bed that slides on that axis, leaving the printing head just move on the x-axis and on the z-axis. As opposed to this traditional approach, a Core XY system has the printing head moving in the XY plane and then has the printing bed moving on the Z axis to lower and raise itself in order to get the upper layers of the print. I decided to go with the Core XY approach as it offers a lot of precision on the X and Y axes and more than decent precision on the Z axis. As opposed to the traditional orthogonal system, which uses a motor for each of the X and Y axes, the Core XY system uses some geometrical voodoo that moves the printing head using 2 motors on the XY axis, but there's no connection between a motor and a certain axis. The Z-axis movement is controlled by lowering and raising the printing bed, which is the surface on which the print lies, and the separation between the XY plane and the Z-axis should, in my opinion, lead to better quality of prints. Now, moving stuff around, like carriages or gantries, the print head itself, along the 3 axes, is a whole lot simpler if you use something called linear motion guides. As the name implies, what they do is they prevent motion in any other way than along that specific line that you're trying to move the thing on. This would help steppers do their job with a lot less effort. It prevents any wobbling and any imperfections. Traditionally, cylindrical rods are used for this, but I think I needed a bit more precision, so I opted for some light industrial grade linear guide and motion carriage. And I'm hoping that this would produce better prints, but I do have to make sure they are perfectly perpendicular to each other along the 3 axes. Regarding perpendicularity, I've read it's crucial to have perfectly perpendicular axes along which the printing head moves. If you don't, you'll get skewed results at best and worn printer parts at worst. It's also a lot easier to debug problems if you have those things set up very straight. Traditionally, and I'm talking here about very well-known designs like the Prusa i3 or the Ender 3 types of printers, you have a gantry carrying the hot end on the x-axis and moving it up and down on the z-axis, and a bed sliding on the y-axis with the print on it. While decoupling the x and y axis movements is, I think, a very good idea, I don't think it's a good idea for the print to move in very ample motions along the y-axis until it's set, as this may introduce some wobbling or ripple effects in its outer walls. The best approach would be to have the printed part stationary and move the hot end, the extruder, on the x and y axes, but then again moving something heavy along the x and y axis would also introduce ripples in the printed part. As with anything in engineering, it all comes down to compromise, and I think that having the x and y carriage stationary in a vertical plane and having the printing bed raise or lower with the print in very fine increments, like a layer height and no more than that, I think that will produce the best quality prints. Now, putting all of this information together, I think I figured out that for me, a cube-like structure with an independent printing bed that can move inside of the cube vertically made the most sense. I would like to be able to keep the hot end of the extruder stationary in a vertical plane, so it doesn't move vertically, it just moves around on a horizontal plane, and then have the printing bed raise or lower with the entire print. I think that makes the most sense, and it also would help with being able to enclose the entire cube-like structure, because there may be cases where you print very specific materials like ABS where you need to regulate the temperature within the printing chamber, and it's much easier to build an enclosure around a cube basically. To have great print quality, you need very fine grain control, very big resolution as it's called. Think of your phone camera from 10 years ago and the one you have now. Look at one of those photos from 10 years ago on the same monitor where you would look at one from now, and you will see that each individual pixel is a whole lot smaller on your current day phone than on the ones you had 10 years ago. And that means that you have a bigger resolution, a finer grain control for each individual pixel. It's the same thing with 3D printing. You need to be able to move in very small increments the entire printing head in order to achieve a good quality. There needs to be a mechanism that takes in a 3D model and it chops it up in small instructions to the stepper motors, which in turn move the printing head around, heat up an extrude filament, and then let it drip, settle, and turn into a final 3D printed part. This mechanism is not within the 3D printer itself. It's a piece of software that runs on your computer, which is called the slicer. Its output is a set of instructions in a language called G-code, which when interpreted sounds like move the stepper motor A so that the gantry moves along the x-axis for 5 millimeters at a rate of 2 millimeters per second. However, the motor in question needs to be able to accurately, quickly, and silently obey the instruction it gets from the slicer. While most of that moving capability lies within the motor itself, the actual interpretation of the instruction and sending it over to the motor lies within the beating electronic heart of the 3D printer, which is the mainboard, and its sidekicks, which are the stepper motor drivers. The mainboard must be powerful enough to handle tons of such instructions each second, because there's a lot of moving around going on, while the stepper drivers need to be able to precisely move those motors in even smaller increments than the nominal step of a motor. Now, after reading around, I found that using traditional 8-bit microcontrollers for the mainboard is a bit too imprecise, and I wanted to go to a 32-bit mainboard option. I also wanted a quick way to send G-code instructions from the slicer on my PC to the 3D printer, so I decided that the mainboard must have networking capabilities in the form of either Ethernet or Wi-Fi. Now, a lot of what I just said has come to me as a conclusion after viewing or reading dozens of 3D printer reviews. But once I had a big enough set of criteria, it was a whole lot easier for me to make a decision about what 3D printer I should buy. I finally settled on a design that I think is sturdy enough, precise enough, affordable enough, and extensible enough for me to modify in the future if I don't like it. And that's the BLV MGN Cube. BLV stands for its designer, Ben Levi, whom I'd like to thank for putting out such a good printer design. MGN is the name of a linear motion carriage made by a Taiwanese company called Highwind, and that's the MGN 12 linear guides. And Cube obviously stands for its round shape. Time will tell if my choice was correct. I'm pretty happy with that at the moment. The point is that you always have to pick what's best for you. There's no such thing as the best 3D printer. There's always a good 3D printer for your particular needs at the time. And it's always an engineering compromise between your needs and your constraints. And those constraints might have to do with price, the overall size of the 3D printer, its print quality, or some very specific aspect like it needs to have Wi-Fi, for example, because that's what you really need. There's no such thing as a good for everyone printer. You have to sit down and think about your constraints and think about your needs and think which one is the best for you based on the research that you can do. I have already received most of the parts for my 3D printer in the form of an affordable DIY kit from China. I have done nothing to put them together yet. I will do it together with you in a mini-series on this channel. Just so you know, I bought some extra parts from Europe as well, because I thought that some parts needed swapping with something of better quality. This video could have been a lot longer if I drilled down into every technical aspect that I mentioned. Now, I could go ahead and create videos on that if you're interested. Let me know down in the comment section. Until then, let's get together soon and start building the BLV MGN Cube right here on A Professional Noob. Thanks for watching and see you soon.